Hey guys, welcome to part 1 of our lesson on section 8.3 vectors for Math 112. The reason this is going to be a two-part lecture segment is because we are dealing with a new concept of vectors, and there's a lot of kind of base definitions and ideas that I want to get in here in this first video before we get into some of the real meat and potatoes in our next video. For those of you who have been keeping that kind of second note sheet with all of those kind of key concepts, make sure you guys have that out because there's going to be a few of them here that you're going to want to make sure to have really distinctly written down and easy to read at accessible places. So when a problem says, hey, find the dot product, you're not flipping through all of your notes. You can just quickly jump into that quick note sheet and be like, hey, dot product is this. This is the calculation I need to do. I don't need to worry about where it comes from, what the derivation of it is, all of the stuff that we're maybe going through in here. You just need to worry about what calculations do I need to do. So if you have that sheet rolling, make sure you have that out to the side. We're going to have a few things that we're going to put onto that sheet. Let's dive into what a vector is. So this symbol here that we've got starting out here, this PQ with a little arrow over the top, that is something that we call a directed line segment. Okay, we talk about a directed line segment is very simply, it is a finite length of line that has a start point and an end point, and it travels in a specific direction. And you can see here in this drawing over here, we start at P, right here, we end at Q, and we are traveling in this direction. Okay, so when we talk about these directed line segments, one thing we want to talk about is the magnitude or the length. And we denote that using, it's kind of similar to an absolute value, but instead of 1, it's 2 lines. And then this is the directed line segment PQ. We kind of do it like that. And then 2 more bars. Okay. So this is represented by the magnitude. And we can find this if we have the coordinates of P and Q, say on our coordinate plane, very simply by using the distance formula. And the distance formula is really just an application of the right triangle Pythagorean formula, the Pythagorean identity? No, Pythagorean theorem. And so it says the distance between 2 points is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, and that's all in the square root. Okay, and you'll see kind of how this is the Pythagorean theorem in a minute. We're going to do an example here in just a second. And so we have this idea of directed line segments. It's got a magnitude or length. We also call these vectors, okay, as it may be obvious by the name of the section. So we would also refer to this as a vector. And so any two vectors that have the same direction and magnitude are considered equivalent. Okay, so in other words, if they are going in the exact same direction and have the same length, then we say that they are the same. A vector can kind of start and end anywhere it wants, and we can really kind of like imagine, if you would, putting a little stick on a graph and keeping it oriented the same way, so it's pointing the same direction, but sliding it around. Everywhere you slide it creates a new vector, and all of those vectors, as long as you've got it kept in the same length, the same angle, is equivalent. Okay, and so I have these two vectors here. This vector here, so this is kind of a symbol we use for vectors. So you noticed up here we used PQ with the arrow. That's a directed line segment. For a vector, we use a single letter to represent the vector with an arrow above it. And you can see that right here and right here. So this vector on top is a vector U. The vector on bottom is our vector V. Okay. And so to find the magnitude, right? So we want to find the magnitude of the vector U, which is equal to the magnitude of the directed line segment PQ, which we can just use the distance formula to do this. So it's x2, so 4 minus x1 squared plus y2 minus y1 squared. That's all being square rooted. And that comes out to be the square root of 8. Now if we find the magnitude of the vector v, and u and v are our pretty common typical vector variable names. Those are usually what we go with. But just like any variable, you can always choose any letters you want, as long as it's appropriate to the problem. So the magnitude of vector v is the same. Okay. As the magnitude of the directed line segment rs, which is the square root of 5 minus 3 squared plus 0 minus negative 2 squared, which also comes out to be the square root of 8. So these both have the same magnitude. Now, do they have the same direction? And the way we calculate the direction is we essentially want to find the slope. And now there's a third component to this after slope, and we'll talk about that in just a sec. So keep paying attention, right? Don't just zone out and be like, slope, yeah, I got this. So the slope of PQ, right? We have 2 points. We have the point 2, 1 and 4, 3. Slope, we know how to do that, right? That's the exact same. We do the change in y over the change in x. So we have here 3 minus 1 over 4 minus 2, which is 2 over 2, which is 1. And then the slope of RS is very simply 0 minus negative 2 over 5 minus 3, which is also 2 over 2, which is also 1. So these have the same magnitude and the same slope. Now, what we have to also look to is, do they have the same direction? Because we could have one vector with the exact same slope and magnitude going this way and another going this way. Those would not be equivalent. So they have to have the same magnitude, the same slope in this case tells us kind of the angle, but we also have to have the same direction, right? If we look back to our definition, any two vectors that have the same direction and magnitude are considered equivalent. So the slope essentially tells us the angle, and then we have to look at the arrow on these things to see what the direction is. Okay, now the most convenient representation of a set of vectors is the vector with its initial point at the origin. Okay, so if any vector that has the same magnitude and direction is equivalent, then we can take any vector and make its original point the origin. Okay, that way we just have to represent it with the terminal point. Okay, and the way we do that, the standard convention that we would write this vector is with these kind of angled brackets like this. So if I wrote something like say like this, say 3, 2, this would be the vector starting at the origin that ends at the point 3, 2. And so we would draw that roughly about here. Oops. Just like that. Given that this here is the point 3, 2. Okay, so that would be how we could represent that vector. And so this is a pretty standard representation of a vector, is these kind of angled brackets 3, 2. If you're doing MyOpenMath or other computer softwares and you want to do these angled brackets, it's the same, usually the same button as the less than and greater than buttons. And so you just kind of bracket it with that, and the software is built in to recognize what you're doing. So let's use the graph to write the vector using its most convenient representation. In other words, I want to find the equivalent vector to this vector here, PQ, that has its initial point at the origin and goes from there. And so the way we can do that is we can really just think of this as moving left and right and moving up and down. So I know I want the initial point to be at the origin. So that means the initial point, which is at 1, -2, it needs to go back to the left 1 space. So that means Q would need to go back to the left 1 space. Now, since it's at 1, -2, it means it also has to go up 2 spaces. That means Q would have to go up 2 spaces. So let's tack on another 2 tick marks there. And so that makes this end point be at the point 2, 4. And so then our vector, our equivalent vector is this here. And so we would say that is the vector 2, 4. So that's really the easy way to think about how to do these. If you're given a vector somewhere else, think, okay, well, the x value of the initial point was 1. So I need to take 1 away to get it to 0, which means I also have to take 1 away from the terminal point to make sure it's the same vector. And that's really all we do. It's really that simple. Okay. All right. So this kind of format that we've been writing in, this arrow 2, 4 kind of thing, is considered the component form of the vector. And so if we have a vector, let's see here. So we have initial point P, which is the point P1, P2. Right? That's kind of our X, Y. And terminal point is Q, which is at the point Q1, Q2. Again, kind of our X and Y. We can say that the vector created by that, the vector V, is equal to the directed line segment PQ, which is equal to, and we're going to use these kind of arrowed brackets. And it's kind of similar to what we did with up here. Never mind. Nope. Never mind. Not similar up there. But it's just, so the X value of it is Q1 minus P1. So it's kind of what we did up here, right? P1 would have been our X value here. So we had to take 1 away. So we took 1 away from the Q1, or 3, to get us 2. And then the other component is Q2 minus P2. Okay. And what we'd say is, since this is now the vector V, we would say this is the component V1, V2. Okay. So you can see really quickly, right, V1 is equal to Q1 minus P1, and V2 is equal to Q2 minus P2. Okay, these are called the components of the vector. So when you're given 2 points, when you're given a directed line segment and said, what's this vector, especially if you want to say it in its initial state, or when in the most convenient placement, this is how we can find that very quickly. So if we think about the magnitude here, our magnitude, if we go back to our distance formula for these 2 points, is Q1 minus P1 squared plus Q2 minus P2 squared. And if we look at what Q1 minus P1 is and what Q2 minus P2 are, we can see that this is really just V1 squared plus V2 squared, the square root of that. And so when we're given a vector in this kind of convenient form, right, where its initial point is the origin, to find its magnitude, we simply take the square root of the sum of the square of its components. That sounds really great. So it's the square root of the sum of the squares of the components. So in other words, taking the square root of adding these things together. The things we're adding have been squared, and the things that are being squared are the components. So that's kind of that's one way we would kind of say what this thing here does. This is the square root of the sum of the square of the components. Makes it sound really crazy, but it's really very simple. quick note on this. Another quick note. So we say two vectors are equal if their components are equal, right? So if the vector v, which is the v1, v2, and u, which is u1, u2, are equal, then we have very simply that v1 must equal u1 and v2 must equal u2. Very cool. This isn't really anything crazy new, just kind of really application of what we just talked about, right? So the magnitude of the vector v is equal to what I just said, right? The square root of the sum of the squares of the components. Okay. If the magnitude of a vector is 1, we call that the unit vector. And if it is 0, okay, then that means its components are going to be the components 0, 0. And we call that very simply the 0 vector. And typically, instead of saying that's the vector v, we actually write that as 0, with a vector over it. Okay. So I want to find the component form and magnitude of the vector with initial point 1, -3, terminal point -6, -8. So it's really easy when we're on a graph, because this is really literally the exact same thing as this, just adding into that the magnitude. It was really easy here because we were able to kind of visually see what we needed to do, but we can just follow these few kind of things right here and get this very simply. So it doesn't give us a vector name, so we're going to go with the vector v, because why not? So the vector v is going to be equal to, so it's just q1, the terminal point, minus p1, so it's, don't really need that, -6 minus 1, and then q2 minus p2. -7, and then -8 minus -3 becomes -5. So there's our vector. Okay, now to find its magnitude, the magnitude vector v is the square root of -7 squared plus -5 squared, which is the square root of 49 plus 25, is equal to the square root of 74. Okay, that's it. We don't need to, rationalize or factor anything out of here or do any of those kind of square rooty things. Really, when we get magnitude, just leaving it like that is perfectly okay. So if you had something like the square root of 24, right, we don't need to say, oh, that's just 2 root 6, right? And so for those of you who are going like, how is that 2 root 6, right? 24 is 4 times 6. Square root of 4 times square root of 6. Square root of 4 is 2, so we get 2 times the square root of 6. For those of you who have totally forgotten this part of math, pulling out, simplifying radicals like this, I'm not worried about it. We're not going to do it too much in here. We're just going to leave it as square root of 74. So now what I want to do is I want you guys to try to do this right now. Okay, so this is scalar multiplication. I want you to just do this in with your intuition. What do you think this is going to do? What do you think is going to happen? So we have the graph of the vector u right up here. Okay. I want you guys in each of these boxes to draw, what do you think 2 times the vector u is? What do you think 1/2 times the vector u is? What do you think negative u would be? What do you think -2u would be? And I want you guys to draw those out and see if you can kind of guess what they would be. Now pause the video. Don't have to get a ruler and get a compass and match the angles, just approximations, right? So we can kind of visually see this. So pause the video, try to do it. Use your intuition. If you need to split these boxes in 2 so you can have your guess and then what we actually do, great. Pause the video. I'm going to drink some coffee now. All right. Welcome back. So, 2u. Well, when you multiply things by 2, what happens? They usually get bigger. And lo and behold, that's exactly what happens here. So, u was, say, about 1 pinky tip length. So we're going to go about 2 pinky tip lengths. Half means we're going to go about a half as far. Negative means we are now going in the reverse direction. And -2 means we're doubling and going in the reverse direction. That's all it is, right? It really is that intuitive. It's that simple. And so it's really not something too crazy or complicated. So now we'll further develop scalar multiplication. So for those of you who are confused about what a scalar is, a scalar in this context just simply means a constant single numerical value. So a number, if you will. So we have these vectors, which are these component things that have an x kind of and a y component, which really represent all these directed line segments. A scalar is just a number. So 5, 2, -1, 1/2, things like that. So we want to talk about vector addition. How do we add vectors together? And it's really simply just component-wise. So if vector u is u1, u2, and vector v is v1, v2, then vector u plus vector v is just simply u1 plus v1, comma, u2 plus v2. And what that looks like, graphically speaking, okay, is if, that's terrible. Okay, that's a little better. So if this is our vector u, and say this is our vector v, okay, the way we add these together is really simply to kind of imagine taking vector v, and remember how we talked about these being like sticks on a graph, and you can slide them all around. And we're going to slide this vector v so that it starts here. So it has the same direction and magnitude, okay? And then that becomes our new terminal point. So now this vector here, this is the vector u plus v. And so that's how this works. And you could do it in either order, right? If you wanted to think of, if you will, taking the vector u and adding it onto the vector v, we end up, I don't want to mess that up too much, so we end up right here. And so it doesn't matter which order you add these, which is a really cool and very crucial, important component to these, to vector addition, is that it maintains the same ideas as basic numerical addition, which makes sense because all that's happening here is we have component-wise addition, okay? So it doesn't matter whether you do u plus v or v plus u. Either way, you end up with the same resulting vector. What about u minus v, right? Well, an easier way to think about this is to change this to addition, okay? And so what I mean by that is we have the vector u minus the vector v. That's the same as the vector u plus negative the vector v. So if I think about a graph, okay, and let's say this is u, and let's say this right here is the vector v. Actually, I want to do that in black. And let's say this is the vector v. So then negative v would simply be, and that's our vector negative v. So if I add these two together, again, we're just thinking of the stick, we move it, right? So I add this, I take this vector v, I attach it here, and it really wouldn't have gone that far. I go to about here, giving me this resulting vector, which is the vector of u minus v. So the way we do that, say, component-wise, is very simply, is the vector u minus the vector v is equal to u1 minus v1, u2 minus v2. And you can see from this reason, it's not the same necessarily if we do u minus v versus v minus u. You see, if we take v minus u, so we take this negative u, which would be this guy here, attach that to here, we'd end up with this resulting vector. And we can see that those two green vectors are not the same. Okay. And so it does matter the order when you are doing subtraction of vectors, just like it matters if you do the order of subtracting any two numbers. Okay. Let's look at a nice little example here. So we are given this little sketch where we have v and u. Okay. So we've got v here. We've got u here. If we want to just sketch the following, just create a little graph. Okay. So the vector u goes about there. Then we're adding to that the vector v goes about there, giving us the resulting vector here. Bam. What about u minus v? I've kind of already done both of these, so these are pretty easy ones, right? So again, we're starting with our vector u. So we start with our vector u, but this time we are going to subtract our vector v. So that means I want to think about what's this negative v is something like this. So that means we're simply going to go something like that, giving us this resulting vector. I don't know that that's right along the x-axis. It kind of looks like it does. I'm also just not drawing super accurately. It may be right along there, and that's totally fine. It may not be. Judging by the original image, I would say that it doesn't look like they have the same y value, so I'd assume it would be a little above the x-axis. But that's something that in a more specific context, we're given the coordinates of these things, and we're able to accurately graph them, we would know more precisely what's going on. Negative 3v. Okay. So not only are we making v negative, so we're flipping it around, but we're also multiplying it by 3. So it's not just negative v, but it's negative 3v. Okay. Again, we're going to start with our u. But now we're going to add half v. So when we added v, we saw that we got like that, but now we're only going to half of v. So we're only going to go like this, just a little bit, giving us our resulting vector. Last but not least, we have v minus 2u. So if we look up here, u is this, so 2u would be a pretty long one like that. And so you end up with something roughly that. It might be a little longer, but that's okay. And there's our resulting vector. Okay. Notice all of these are sketches. None of these are exact, precise drawings or anything like that to scale or anything. We're just kind of getting a rough idea of kind of what these do. And so in all of these, the green is our resulting vector. The green is the end result of what the mathematical operations that we performed on these vectors. So we have vector addition. Now let's talk about scalar multiplication. Scalar multiplication, so for some number k, for some scalar, I'll just put in parentheses, which is just a number, k times the vector v is simply equal to k times v1 with k times v2. That's it. That's all we're doing. Okay, it's just component-wise multiplication. So addition and subtraction and multiplication are all just component-wise, right? We just, if we're adding two vectors, we add the kind of x's, and then we add the y's. If we're subtracting them, we subtract the x's, subtract the y's. If we're multiplying by a number, we just multiply the x by that number, then multiply the y by that number. It's really just that simple. So let's look at another example. We're going to break this down a little bit further, and I'm going to go ahead and quickly just chop this up. So we know what u is. U is the vector 2, -3, and v is the vector 4, 7. So to find the following, we just use what we know. So u plus v is asking 2, -3 plus 4, 7, so that is just equal to 2 plus 4, -3 plus 7. And so we end up with the result 6, 4. U minus v is just going to give us 2 minus 4, -3 minus 7, which is going to give us the vector -2, -10. Right, so far, really easy. Now, this next one gets a little more complicated. Totally doable in your head if you want to, but I like to I'm going to step it out a little bit. So this is equal to 2 times 2 -3 minus 1/2 4, 7. And so that's 4 -6 plus -2 7/2. Okay. If you want to go with fractions, you can, but or if you want to go with decimals, you can on this one, because 7/2 is just a nice clean -3.5. But always stick with fractions. Is a lot easier to deal with, a lot better because it's a lot more precise. You don't have to worry about, is this a fraction I can do it as a decimal, or is this something like 7/3, in which case don't do that as a decimal until the very end if you have to. But now we just subtract these, add these, and we end up with 2 and -19 halves. For those of you who are panicking, that's just -9.5. All right. Pretty easy. Pretty straightforward. Now here I'm going to go through some properties. So what we're doing is we are assuming that that u, v, and w are all vectors, and c and d are scalars, so they're just some numbers. Okay. So some nice properties we get is that vector u plus vector v is equal to vector v plus vector u. And vector u plus vector v, then plus vector w, that's the same as vector u plus the quantity vector v plus vector w. Vector u plus the 0 vector is just vector u. It's a terrible vector. Vector u plus negative vector u is just the 0 vector. C, so this is our scalar, so the scalar c times the scalar d times the vector u is just the same as c times d times the vector u. If I have c plus d times the vector u, that is the same as c times u plus d times vector u. So what's really nice there is that one right there tells us that we can distribute a vector across scalar addition. Okay, and c here gives us where we have a scalar times vector addition, and we can also distribute a scalar across vector addition. Okay, 1 times vector u is just vector u. 0 times vector u is the 0 vector. And this is a cool part here. The magnitude of c times vector v is equal to simply the absolute value of c times the magnitude of vector v. So that's really kind of nice, is that if we know what the magnitude of v is and we multiply it by a scalar, all we're really doing is multiplying the magnitude by that number as well, by that absolute value of that number. because magnitude is, if you remember back up to their definitions, it is a length. And so we want to be treating that as a measurement of length. And if you remember anything, if you had 111 with me, you know that lengths can't be negative, and hopefully you just know lengths can't be negative. But we'll do the same. Let's do that. Let's do it. Let's take a break from writing, put our pencils down, shake our hands out a little bit, put your hands about 1 foot apart. Now move your hands so they're a negative foot apart, right? I'm sure some of you maybe crossed your arms or something like that, right? But those are still just a foot apart. You just have your arms crossed like a weirdo. So there is no negative distance, okay? That's why magnitudes are always going to be positive. All right, almost done with this first video. Let's do a nice little example. So unit vectors, a unit vector u in the direction of v is given by blank. So we need to figure out, this first part is trying to figure out how can I identify essentially not an equivalent vector, but a unit vector. Unit vector is just like the unit circle in our previous lessons has been very important. Unit vectors are very nice to deal with because their magnitude is 1. So how can I make it so that I have the same direction, but my magnitude is 1? Well, this really simply relies on 10. So if I know that the magnitude of CV is equal to the absolute value of C times the magnitude of V, and I want this to equal 1, what does C need to be? What do I need to multiply this vector by? What scalar do I multiply this vector by to get that? Well, remember, magnitude is just a measurement. It's a single number. So I can divide by the magnitude of V on both sides, giving me the absolute value of C equals 1 over the magnitude of V. Now, we are told that means that this could either be positive 1 over the magnitude of V or it could be negative 1 over the magnitude of V. But we want it to be in the same direction. So we want to use the positive. So that means that, so a unit vector u, so u is the unit vector, okay? So that means u, vector u, is just equal to 1 divided by the magnitude of the vector v times the vector v. Okay, if you want to put these together, you could say this is the vector v over the magnitude of the vector v. I quite frankly don't like that. It doesn't give us that good scalar multiplication ideas. So I'm just going to leave it like this. So now what I want to do is I want to find a unit vector in the direction of v equaling 5, negative 3. So what I have to do is I have to find the magnitude of v. So to do this, I need to find the magnitude of v. And that's equal to the square root 5 squared plus negative 3 squared. 25 plus 9 square root 36. Sorry, 34. I can do math too. It's okay. So we know what the magnitude of v is. So that means that u is equal to 1 divided by the square root of 34 times the vector v. So that's going to be 5 over root 34, comma, negative 3 over root 34. And that's it. And now I'm going to leave it to you. I want you to check this. So what I'm saying is find the magnitude of u. I want you to actually use your calculator, put in these numbers, square them, add them, take the square root of that, and see what you get. So make sure it is 1. If it's not 1, email me because I did something wrong. I didn't. So if it's not 1, double check your mathematics, make sure that you're actually doing everything right, and you're good to go. All right. So let's see here. Stop here. Don't want to keep going. I think I'm going to stop right here. I'm going to stop right here with you guys. This will be the end of video 1. We'll see you back starting with standard unit vectors for video part 2.